When a high-voltage transmission line is severed or struck by lightning, the electrical power grid experiences a short-circuit fault. This is an immediate, catastrophic event where massive currents bypass their intended paths and surge through the network infrastructure. The resulting fault current is a violently dynamic, asymmetrical waveform that evolves constantly throughout the event. It is a shifting sequence of values that changes its behavior millisecond by millisecond. This chart shows the two main components of the fault current. The first is the DC offset. Because grid circuits contain inductance, the current cannot change its magnitude instantaneously, creating a direct current shift. This offset decays exponentially to zero over the first few cycles, dictated by the network's specific ratio of inductance to resistance. The alternating current envelope sits on top of that offset. The amplitude of these AC peaks shrinks rapidly before eventually leveling out, decaying through three distinct temporal phases. To understand why this AC amplitude shrinks and why it dictates the survival of the grid, we have to look inside the physical architecture of the generators feeding the current. This is a cross-section of a standard synchronous generator. The stationary outer ring is the stator, separated by an air gap from the spinning rotor. The rotor contains two specific winding layers, the outer damper windings and the inner main field windings. At the exact millisecond a short circuit occurs, the stator demands a massive, instantaneous increase in current. This generates a sudden surge of magnetic flux that attempts to cross the air gap and penetrate the spinning rotor. The rotor's internal magnetic circuits provide physical opposition to this armature flux, forcing it to bend into high-reluctance leakage paths. This opposition is defined as reactance. This magnetic opposition weakens through three strict temporal phases: subtransient, transient, and steady state. These internal machine phases serve as a timeline, directly controlling the scale of the physical threats unleashed on the wider grid. The timeline begins at zero, marking the initiation of the subtransient period, which lasts for roughly 20 milliseconds. Under Lenz's law, the rotor's outer damper windings instantly induce their own currents to oppose the sudden change in stator flux. These currents block the flux at the very edge of the rotor. Because the flux is constrained to the outermost leakage paths, this initial state presents the lowest effective magnetic opposition, known as the subtransient reactance, or X''D. Reactance is inversely proportional to current. This low reactance value allows the absolute highest peak of fault current to flow out into the grid. This massive current peak generates extreme electrodynamic forces across the network. The magnetic field surrounding the conductors becomes so intense that rigid substation busbars can violently shudder, warp, or even rip themselves from their mounts. Simultaneously, the grid experiences massive, rapid thermal heating. The energy dissipated is proportional to the current squared, which can rapidly degrade the insulation in high-voltage cables and switchgear. The subtransient phase is a brutal test of the physical, structural, and thermal limits of the grid's heaviest hardware. As the fault continues past 20 milliseconds, the induced currents in the damper windings die out due to their high electrical resistance. This marks the start of the transient period. Without the damper windings actively opposing it, the stator flux pushes past the outer edge and penetrates deeper into the rotor, reaching the main field windings. These deeper windings now provide the opposition. This secondary state is the transient reactance, or X''D. This reactance is a higher impedance than the subtransient state, causing the fault current amplitude to shrink. While the physical forces decrease, the fault has now drastically reduced the generator's ability to output electrical power to the network. This creates a severe mechanical mismatch. The electrical power leaving the generator has plummeted, but the mechanical power driving the turbine remains completely unchanged. With more power coming in than going out, the massive generator rotor physically accelerates. Its rotor angle increases relative to the synchronous grid. The transient phase is a race against time. If the fault is not cleared before the rotor angle advances too far, the machine will suffer a total loss of synchronism. Once the fault persists past 500 milliseconds, the induced currents in the main field winding completely decay. The stator flux now fully and freely penetrates the entire rotor core without dynamic opposition. This final, highest impedance state is the synchronous reactance, or XD. It is governed purely by steady-state armature reaction, resulting in a flat, constant sine wave. Out on the grid, this sustained steady-state current causes severe, prolonged voltage sags across the network. Heavy industrial induction motors will stall under these conditions, drawing massive reactive power and driving the system voltage even lower in a cascading collapse. If a fault persists into the steady-state phase, system protection will trip the generator offline to save it. This triggers a sudden loss of generation and a high probability of a wide-area blackout. Modern power systems are engineered to prevent a fault from ever reaching the steady-state period, avoiding total voltage collapse. Substation protection relays are programmed using the specific subtransient and transient reactance values of the local generating stations. These relays command the circuit breakers to mechanically open their contacts and quench the fault arc entirely within the narrow transient window. The heavy interrupting capacity of these breakers is explicitly sized to survive the brutal peak currents dictated by the machine's subtransient reactance. A generator's shifting internal magnetic layers dictate the precise behavior of every fault current. The subtransient reactance tests structural strength, the transient reactance tests synchronous stability, and the steady state marks system collapse. Mastering this dynamic reactance decay provides the foundational mathematics required to protect the stability of the entire interconnected grid.